Halogens NCRT Part 2. Remember, reading of NCRT is enough for all inorganic chemistry chapters, all groups. So don't go beyond this, even for IIT Advanced also. Believe in my words. Okay? All the questions are interrelated only. So if you are perfect at all these reactions, that is more than sufficient. So try to be perfect in this. Oxidation states and trends in chemical reactivity. Actually, as these are non-metals, you can expect here -1 oxidation state, and +1, +3, +5, +7 is also possible. When is +7 is possible, +1 is possible, +3 is possible? Let us see. In the ground state electronic configuration, this is ground state configuration, Ns2 Np5, one unpaired electron is there. Because of this unpaired electron, it shows -1 or +1. And when you are going for first excited state, this electron is jumping here. Now we have 3 unpaired electrons, so it shows +3. Remember, in the excited states, it shows only +3 because excitation means it is happening only in the presence of highly electronegative atoms. So highly electronegative atoms only make them excite. So in that cases, +3 is only possible. Second excited state, this electron is jumping here. So number of electrons are 5 unpaired electrons, so it will be +5 oxidation state. Third excited state, this electron is also jumping. So you will be having, this is a wrong thing, NCRT mistake you can say. So 1, 2, 3, 4, 5, 6, 7. So 7 +7 oxidation state. Okay, sorry for this. The higher oxidation states of chlorine, bromine, and iodine are realized mainly when the halogens are in combination with the small and highly electronegative atoms, as I was showing you now. That is in interhalogens, oxides, and oxyacids. Otherwise, lower states are only possible. The oxidation states of +4 and +6 occur in the oxides of oxoacids and chlorine and bromine, like Cl2, O6. You can expect, or BrO3. You can expect +6 oxidation state. The fluorine atom has no d orbitals in its valence shell and therefore cannot expand its octet. So its oxidation state is -1. All the halogens are highly reactive. We know this very well. They react with metals and non-metals to form halides. The reactivity of the halogens decreases down the group. So fluorine greater than chlorine, bromine, and iodine reactivity order. One very important point. The ready acceptance of an electron is the reason for the strong oxidizing nature of halogens. Fluorine is the strongest oxidizing halogen and it oxidizes other halide ions in solution or even in the solid phase. In general, a halogen oxidized halide ions are of higher atomic number. Or simply, in other words, you can say top halogen displaces bottom halogen. Top halogen displaces bottom halogen. That means fluorine can displace chlorides, bromides, and iodides. Chlorine can displace bromides and iodides. Bromine can displace iodides. Iodine cannot displace any. So you can see here the same expressions are mentioned here. The decreasing oxidizing ability of the halogens in aqueous solution down the group is evident from the standard electrode potentials, which are dependent on the parameters indicated below. Okay, this we were discussing in the last class only, part 1. You can see I have given complete explanation of this. See, X2 is converted to X, means this is dissociation. And then you are adding electrons, so this is electron affinity. And then you are putting this in water, this is hydration. This is exothermic step. This step is exothermic step. Dissociation is endothermic step. So favorable condition means, whenever, what is the meaning of favorable means? When we are giving, it should be less. When we are taking, it should be more. Like students, when you are studying, it should be less, but when you are getting rank, it should be good rank. Similar. So it's always advantageous. Okay, now any industry or any job or anything, we should work less, we should get more. Okay, in that sense, it should be less, these should be more. The relative oxidizing power of halogens can further be illustrated by the reactions with water. Fluorine oxidizes water to oxygen, whereas chlorine and bromine react with water to form corresponding hydrohalic and hypohalous acids. The reaction of iodine with water is non-spontaneous. In fact, I minus can be oxidized by oxygen in acidic medium. Okay, now these reactions are important. So about this oxidizing, you can check our part 1. Now come to this one. Fluorine is decomposing water. Remaining chlorine and bromine reacting water to form HX and HOX. That means HCl and HOCl. And iodide, now you see in this case fluorine and chlorine and bromine. Now it is not iodine, it is iodide is converted to I2. So iodide is converted to I2. This is mentioned here. In fact, I minus can be oxidized by oxygen. Anomalous behavior of fluorine. Anomalous behavior means this special character. Okay, now in every home one child or one person will be very special. Every home means I am not saying about a 4 members family, a big family. Okay, now where you are talking about your grandfather family, otherwise you take a class anywhere, one fellow will be special. Here in every group that will be general top element, and here it is fluorine. So what happens with fluorine? Like other elements of P block present in second period of the periodic table, fluorine is anomalous in many properties. For example, ionization enthalpy, electronegativity, electrode potentials are all higher for fluorine than expected from the trends set by other halogens. Also, ionic and covalent radii, melting points, boiling points, enthalpy of bond dissociation, and electron gain enthalpy are quite lower than expected. Okay, now the anomalous behavior of fluorine is due to small size, highest electronegativity, low FF bond energy, and non-availability of d orbitals. All these can be asked in exam. Okay, now it is due to A, small size, B, high electronegativity, C, FF bond, D, non-availability of d orbitals. All of these, only one of these, two of these, like this. Okay, now so small size, electronegativity, low FF bond energy, no d orbitals. Most of the reactions of fluorine are exothermic due to the small and strong bond formed by it with other elements. It forms only one oxo acid. This is always controversy point. HOF. HOF, whether it is oxo acid or not, is always a confusion because fluorine should not form plus one. According to this concept, it is plus one. Okay, now NCRT special. And remaining halogens form number of oxo acids like HClO, HClO2. We'll discuss about that. Hydrogen fluoride is a liquid. HF is a liquid due to strong hydrogen bonding. Other hydrogen halides are gases. HCl. Okay, reactivity towards hydrogen. This hydrogen part will complete now. So when they react with hydrogen, they form compounds like HF, HCl, HBr, HA. If you see this table, it will be easy. See, HF melting point should be less, but it is here only because of hydrogen bonding. Boiling point of HF should be less, but it is highest because of hydrogen bonding. Bond length down the group increases, regular trend. Dissociation energy means stability down the group decreases, regular trend. pKa more means less acidic, pKa less means more acidic. Higher Ka, lower pKa, strong acid. Okay, now just reminding you the ionic equilibrium. So this is strong acid than this one. So down the group increases because bond energy decreases, so it will be done. Now let us see what's mentioned here. They all react with hydrogen to give hydrogen halides, but affinity for hydrogen decreases from fluorine to iodine. Hydrogen halides dissolve in water to form hydrohalic acids. Some of the properties of hydrogen halides are given in table. The acidic strength of these acids down the group, acid strength increasing. The stability of these halides decreases down the group due to the decrease in blah blah blah. Okay, so if you see this table, that's enough. Coming to few more lines. Reactivity towards oxygen. Halogens form many oxides with oxygen, but most of them are unstable. Fluorine forms two oxides, OF2 and O2F2. However, only OF2 is thermally stable at 298 Kelvin. In these two, oxidation state of oxygen is very special. Here it is plus 1, here it is plus 2. These oxides are actually called as fluorides, are essentially oxygen fluorides because of the higher electronegativity of fluorine than oxygen. Both are strong fluorinating agents. O2F2 oxidizes plutonium to PuF6. Remember, NEET students, this is important for you. JEE, they don't ask this. And the reaction is used in removing plutonium as PuF6 from spent nuclear fuel. NEET students, concentrate on this. Chlorine, bromine, and iodine form oxides in which the oxidation states of these halogen ranges from +1 to +7, like HClO. We are discussing about oxides, na? Cl2O, ClO2, Cl2O6, Cl2O7, like this. Okay, not HClO. A combination of kinetic and thermodynamic factors lead to the general decreasing order of stability of oxides formed by halogens. IClBr. Okay, now very interesting. We expect Cl, then Br, then I, but it is ClBr, IClBr. So this point you can notice. The higher oxides of halogens tend to be more stable than lower ones. Chlorine oxide, Cl2O, ClO2, Cl2O6, Cl2O7. I mentioned here are highly reactive oxidizing agents and tend to explode. ClO2 is used as a bleaching agent for paper pulp and textile and in water treatment. ClO2. ClO2 is paramagnetic. Remember this point also. Very interesting, important point. The bromine oxides Br2O, BrO2, BrO3 are the least stable halogen oxides. Least stable. Okay, now this is called a middle row anomaly. This is only mentioned here and exist only at low temperatures. They are very powerful oxidizing agents as they are unstable. The iodine oxides I2O4, I2O5, I2O7 are insoluble solids and decompose on heating. I2O5 is very good oxidizing agent and is used in the estimation of carbon monoxide. Remember this point. NEET and JE both you can check this question. Okay, halogens react with metals. Now reaction with metals will go. Before that, you see this point again. I2O5 is a very good oxidizing agent and is used in the estimation of carbon monoxide. With metals, we'll discuss in another video.